valuable information using some analytical process. See, data is the raw facts, right? When you process this, you get some information. So until and unless you go for processing, it doesn't make really sense. So big data is associated with some V's and C's that define the big data. So 7 V's of the big data, this has been proposed. This is taken from a reference from a researcher. The sources given to you, the paper is beginning with big data simplified. So there are 7 V's which are velocity, variety, volume, veracity, value, and variability. So this author, they have proposed a new V, that is the viability. So let's briefly touch upon these 7 V's quickly. So volume, it refers to the large amount of data that is being generated from different data sources contributing to the big data, and that too in a real-time environment. Variety refers to the data that is coming from varied sources, because see, there are a lot of sources which are contributing to big data, so you get a lot of variety in data. That is, there is no structured format. Some can be structured data, some can be completely unstructured, or it can be a mix of semi-structured, right? So there is a lot of variety that is being delivered. Velocity, it refers to the fact that the data is being generated at a very fast rate. Okay, so this we all know that we are overloaded with lot of information across the internet, right? So the data, it is increasing at a very rapid pace, and the speed at which it is being generated is quite fast. So it not only includes the rate of generation of data, but also the time it takes to process the incoming data into the system, and also the frequency with which the data is delivered, right from end to end processing. Then whenever we talk about data, value is one feature which is very important, right? And it is very, very crucial for any organization. Until and unless data doesn't deliver a value, it is of no use, right? So value is one attribute that is again contributed, or that is again applied for a big data. Then we have veracity in big data. It relates to data certainty and trustworthiness in terms of collecting the data, in terms of processing the data, and the trusted infrastructure and the data origin. That is, how can you, with how much trust can you say that this data is accurate? The next V is the variability. Variability causing the peaks in the data load and takes into the account the data that is rapidly engulfing the system. Okay, so whenever you are generating a data and it is engulfing the system, so then we say that we have a load, we have a peak in the data load, because a lot of data is being loaded into the system, right? So this causes a wave effect which requires the data model and associations to be altered to get inferred from the growing data stock. Then viability, this is what they have proposed. So it's a multi-dimensional factor that talks about. So whenever we talk about data, there are multiple dimensions to it. There are multiple attributes and features that are associated with data. And depending upon the kind of application you are developing, not all the features would be important, right? So like if I say that if a data set has got 100 features, so you might not be working on all the 100 features, right? So you will be using might let's say 10 or 20 or 15, whatever. So whenever we talk about viability, it refers to the multidimensionality of the data. So depending on the outcomes, all the dimensions are not relevant during the processing, and then you have to pre-process the data, you have to filter the data, and that we are going to see shortly. Then the 3 C's of big data, it is the cost, consistency, and the complexity. So consistency and cost is what was already there. So complexity is being proposed here. So complexity, it measures the degree of interdependence and the degree of interconnections between the data, right? If you talk about a social media data these days, what is happening? You have a friend, then you have a friend of friends, and that is why, that is the interconnectedness amongst the data. That is a very small example that I'm taking. So there is a lot of interdependence amongst the data, so that kind of data can be regarded as a big data. This is one feature which can help you identify a big data. So this caters to the fact that whether making a small change to one or more elements would result in a corresponding change in the other data or not. So whenever we're talking of complexity, we have to always ensure that the ripple effect, we have to check for the ripple effect. If we change one parameter at one point in time, is it affecting the other interconnected points, other interconnected data points or not? This is one important thing. Then we have the cost. This attribute is complement to the volume attribute of the big data, because the rate at which the data is being generated and the volume at which the data is being generated, it is quite significant, right? And hence big data cannot be stored and processed by traditional databases, and we require altogether a novel technology which comes again with a cost, because then we will be talking about setting up a master slave architecture wherein we will have a cluster, okay, and we have a master, we have all the slaves that will be coordinating with the master and things like that, that I'm going to take up in the upcoming slides. Then the last factor is the consistency, the last C. So consistency refers to the data that flows amongst various sources and it is being shared by multiple users. See, whenever any data is being shared amongst users, there is a high chance that one is accessing it and simultaneously the other one is doing some write operations for it, right? So this
Actually,
kind
ma'am,
of, yes,
hello.
ma'am. Hello.
Actually, the slides are not changing.
The slides are not changing.
We are
Uh,
on to the first slide. Now they are changing.
Ma'am,
Yes.
just a minute, just a minute. Now is it there?
It is not visible at the moment. It is there. We are on to the slide 3 C's of big data.
Yes,
Consistency.
yes,
Yeah.
line number 9, right.
Okay. Thank you so much.
Okay. So is it that the in the I think in the slideshow mode, probably it's not visible to you. Is it that way?
Yeah, maybe.
So ma'am, is it readable in this format?
Yes, it is readable.
So big data, to summarize, we can say that big data handles a large amount of data with varied sources, generating different kinds of variety in the data. The storage capacity of the device has increased with time, but what we need to understand is the time to process the data. Okay, it hasn't shown any significant improvement, and that is when we will have to adopt certain dedicated technologies which are capable of processing our big data. Right. So, what do we expect out of the big data processing tools? Because we have a large data at hand to handle, we have a lot of variety in the data, and the volume also, and the velocity is also quite high. So, what are we looking at? What kind of processing technologies are we looking at? So, the time to access the device can be reduced by reading simultaneously from multiple disks, which is very obvious, because if we are doing a simultaneous read, so it is going to be a little faster. Right. Significant use of the hardware and relying on that hardware induces a high chance of failure, which can be avoided by making replicas of the data onto different devices. So we can obviously have replicas of the data, and when we have that, so we have to also ensure that the system, the entire system is a fault tolerant one. This can be handled by providing a file system which is organized in the form of clusters, which is comprising of various nodes or servers. So combining data being read from multiple devices is a major challenge that the researchers and the researcher community faces when we are processing and analyzing big data. So selecting a programming paradigm based on a master slave architecture can enable the desired task of combining data from multiple devices and ensuring that it is processed simultaneously, just to ensure that we have a computationally efficient calculations of the processing. The computation should be done near the data. So one feature would be that rather than moving the data around the network, why don't we bring the computation near to the data, right? Rather using the bandwidth for circulating the data amongst the network, it would be better if we keep the data at multiple points and do the processing at those points rather than circulating the data. So that is getting the computation near the data. The processing of big data is made easy by Apache Hadoop, which supports the storage and processing of large data sets across multiple clustered systems. So Apache Hadoop come as a rescue for big data processing, right? And it ensures that we are able to process the data in real time that large variety data, all the features that we have discussed so far for the big data, it is able to handle them. And also it ensures that a parallel processing is being done on the data, right? So let's get into the insight of what is Apache Hadoop and what is the MapReduce programming. So Hadoop is an open source project that is hosted by Apache Software Foundation, and it is an application which is designed to work on distributed systems. Right. So the main components of Hadoop are a file system, which is known as the HDFS, that is Hadoop file system, distributed file system, and this is for storing the data. Right. So you store the data in the Hadoop distributed file system. As the word distributed means that the data, it will be scattered, it will be distributed across all the participating nodes in the cluster, right? And one part is storing, the other part is processing. So how do we process? What programs are we going to write so that we are able to play with the data? We are able to process the data. For that, we use a programming paradigm which is known as MapReduce. So let's talk about HDFS, what it has to offer, and then we will be largely dealing with MapReduce programming. So HDFS, it stores the data in a distributed manner on the nodes, and it is organized in the form of clusters, which consist of several nodes in each cluster. So a cluster is nothing but it is a what combination of several nodes. Now, how do we define the word several? It could be two, it could be three, it could be five, it could be 20, depending upon your requirement, right? So a file is divided into blocks, and then these blocks are stored on different nodes. So since the entire focus of HDFS is to have a distributed storage, so what do? We just take the entire file, we divide it into blocks, and then each block, it is stored on different nodes, and each block is of large size and is of 64 MB by default. But you can of course change this block size, but by default it is 64 MB. So the entire file you are going to split up in the blocks of 64 MB, and then you are going to store it on different nodes which are participating in a cluster. So HDFS, it comprises of a name node, a secondary name node, data nodes to store and manage the data. Right. So look at this diagram. So this is what is a cluster setup. So whenever we are talking about a Hadoop cluster, one thing is that we talk about the masters, and then there are several slaves which are participating in the cluster, which are going to ensure that the processing takes place, the data processing takes place. So in this master node, you can see we have HDFS component, which is capable of storing the data. And on the other side, we have the map reduce part, which is which will be responsible for processing of the data. Right. So one is the storage, which is taken care by the HDFS. So now when we talk of this master slave architecture with respect to the Hadoop distributed file system, so in the master, we have the name node and the secondary name node. And on all the slaves, here we are saying that we have slaves from 1 to n. So this n can be any number. Right. So from 1 to n, on every slave, you can see, yes, there is one data node that is present that is going to store the data on every slave. So आपके पास एक फाइल है, ठीक है? आप उस फाइल को 64 MB के ब्लॉक्स में स्प्लिट करेंगे, and every block and each of the block will be stored in the slave nodes, right? So master is going to take the control, and it is going to direct all the slaves of how to do, what to do, when to do. So name node, it comprises of the metadata for the directories and files residing in the file system. So this is the details of the metadata of which kind of data, what data is stored at which particular slave, and things like that. Right. So data node, it stores the actual data which is present in the slave nodes. Actual data by storing the directory blocks, file mappings, and the namespace tree. The request of accessing data in a cluster is addressed by the HDFS client by sending a request to the name node, which returns a list of the data nodes where all the blocks of the files are residing. And in order to ensure that we have a fault tolerant system, so we are going to create replicas of each block of file on the various data nodes in the cluster. Just in case a slave goes away, we have encountered a failure of a slave. So that should not hamper the entire data processing, and we should not also lose the data that is present on that particular data node. So for this, we have a replicator factor. Now, by default, that replication factor is 1. You can change it to 2, 3, and depending upon how many nodes you have. So that each block it is replicated on to that particular number of nodes. Then we have the secondary name node, which helps to recover from the data from the name node failure by keeping an updated copy of the namespace image, which can be used just in case the name node fails. Because see, over and above, it is a system. Okay, it can fail also. A name node can also fail at any point in time. A data node can also fail. So we have always have to keep a backup. So we have a secondary name node for that, which is going to keep an updated copy of the namespace image, and just in case we encounter a name node failure, so we can recover the entire system using the secondary name. Now, HDFS is a file system with a Hadoop framework which possesses the capability of distributed storage of data and processing this distributed data residing across the cluster. For this we need a parallel processing programming paradigm, which is catered by MapReduce. So every task that you submit, it is executed in two phases, that is map phase and the reduce phase. So now we are talking about how to process the data. Just now we have finished talking about how to store the data in a Hadoop, Apache Hadoop, that is using the HDFS. Now the data is already there in our cluster. Now we are talking about how to process them. So map reducing is a programming model and processing framework designed for parallel and distributed processing of data sets. So map reduce programs are designed to work with massive amounts of data and perform operations like filtering, aggregations, and transforming data efficiently. So map reduce programming paradigm, it is one paradigm which ensures that you are able to process the data in parallel. Processing takes place in parallel because we have large number of data items with us, a huge amount of data, and in order to ensure that we are, doing it parallelly, we are doing it efficient processing of data. So we have to go in for some parallel programming paradigm, which MapReduce offers us. So parallel processing, it is useful in performing a data-intensive task where a task is broken up to multiple parts with a software tool, and each part is distributed to a processor, and then the processor will perform whatever is the assigned task. Then another paradigm is the load balancing, in which each machine will get an equal share when dividing the data into chunks, so none of the machines is being overloaded or underutilized. ऐसा नहीं हो that we end up loading one of the machines so much that most of the machines or few of the machines are sitting idle. They don't have anything. So we have to ensure that we go for a proper load balancing across the cluster. Then we have the critical path problem, which is managing the time required by each machine to finish the job. If any of the machines fail to deliver the job in time, then the whole task gets delayed. Because it might happen when you're working in a cluster, right? When you're working in a master slave architecture, few of the slaves are quite fast and they have finished their task, whereas majority of them are slow, and then amongst them the speed doesn't match. The time to require the job to the time to require to finish the job is different. So in that case, one would be finishing first, whereas that machine will have to wait for all other machines to complete their task and then go ahead. So this is one thing which we have to ensure, and this is offered to us by the MapReduce programming paradigm. Then we have reliability. So there should be a mechanism to solve the fall of one machine, because if one machine is failed to provide the output, then the whole task will fail. So this also ensures a reliability. Then an aggregation approach should be designed to generate the final task after getting the input from different machines. This is very important because we are focusing on parallel processing. That is, multiple processes will be running in parallel to execute the job. Once everything is done, somewhere something should be responsible to aggregate the result and to show the final output. So this is also one programming paradigm. Now, Hadoop to execute MapReduce task comprises of two types of daemons that controls the execution of the task. that we have already seen in the diagram, that is a job tracker and a task tracker. So let me just again show you this. So now we're talking about the map reduce programming. So on this master slave, in the master node, we have the job tracker, which is going to take control of all the processing that are taking place in all the slave nodes, and the task trackers are responsible for processing the data in the individual slave nodes. The master executes the job tracker, which coordinates and controls all other slave nodes by running task tracker to accomplish the assigned task. Master node processes the input data by dividing it in fixed size units identified as split, and each split is processed on the slave node by executing the map task. So on every split, that is on every data block, we are going to run the map and the reduce task. And the master node, the job tracker is responsible to assign to coordinate with all the task trackers which are running on the slave nodes. The input to the map function is of the form of a key value pair. So this is what we are looking at. This is the kind of input that we have to give whenever we are talking about any map reduce program. That is, it is always going to take the input in the form of key value pair, which processes it to generate the intermediate output again in the key value pair form only. The intermediate output is written out to the local disk, which is given as input to the reducer for further processing. So when we talk about map reduce programming paradigm or programming, so first we have to write the map function. Okay, and the input to the map function will always be in the key value pair form. The output would be generated after executing all the mapper functions. That will also be in the form of key value pair, which will be given to the reducer to generate the final output. Right. So this we're going to see in detail. How is it being done? So depending upon the map reduce framework you are using, various programming languages can be used to write map reduce code. So it's not that just one or two languages are supporting this. You have a choice of programming language, and that often depends on the specific map reduce framework, its ecosystem, and also the obviously the preference for the development team. If you know Java, so you will always be comfortable in writing codes in Java. So this is a list of MapReduce programming language. So we can write it in Java, we can use Python, Scala, Ruby, Go, R, and C++. Depending upon your ease, your comfort, you can opt for any of these. So MapReduce offers the advantages of data locality. So data locality is bringing the processing to the unit. Rather than moving the data around, why don't you take the data to the processing unit? So performing computation process on the site where the data is residing is what by data locality. Rather than sending the data to the processing unit, data locality significantly reduces the network traffic and also the running time. Now, whenever we write any MapReduce program, what are the execution phases that happens? You have written a program using a MapReduce programming paradigm, right? So how is that processing will take place? First step is the input split phase, where your entire data, it would be divided as I have told you. That will be splitting of the data, entire input data. Then second is going to be the map phase, wherein the data will be taken in the key value form. The mapper will execute its desired function depending upon the application that you are looking at. And then it is going to give you an intermediate result again in the form of key value pair, which will go into the next phase of shuffling, sorting, and grouping phase, where the data will be sorted key wise, and shuffling will take place, and also grouping of the data will take depending upon the key. Then finally is the reducer phase, which is going to reduce or aggregate the data and generate the final output. So we will see each of these phases in detail. So first phase is the input split phase. In this step, the raw input data is being divided into chunks, which is known as input split. That is, you have a large data. What you're going to do is you're going to split the data. You're going to divide the data into small chunks, which are known as split. Right. Now, what should be the split size? It can be between 16 MB to 64 MB. And it can, obviously, it can be defined by the user. If you want a large split, Because if you feel that you have a large data and the number of clusters, the nodes in the clusters are less, so you can go for a much higher split, right? So that is completely depending upon the user. Whatever the developer wants to have the size of the split, he can easily have it. These chunks are typically larger than individual records, but small enough to be processed efficiently by individual mappers. So no matter you create the splits, but you should always ensure one thing, that obviously the entire file would be, the entire size of the data will be quite long. And when you're splitting the data, it should be that each split should be successfully and efficiently being executed by the mapper. So each split will be processed by individual mapper. Typically, an input split will have the size between 16 MB to 64 MB, which I just told you that it can be user defined also. And data input of this step will be from in the form of key value pair. So you have key and value pair. This is what is your input data. Let's say there is a large. Let's look at an example of how to map this phase in a problem in an application. So let's say there is a large text file containing a collection of books, right? So the file is too large to fit into the memory or to be processed efficiently by a single mapper. So what is the rescue? That it's better to have a go for an input split. So to process it using MapReduce, the input data is split into manageable chunks or splits, where each split is assigned to a separate mapper for processing in the next. So the entire data, it is being divided. It is being divided into manageable splits, and then we have to ensure that every mapper is executing every split of data. This is what it is going to do, right? So original input data would be a large set of a large text file containing multiple books, and input data splitting. Just a minute. Yes, and data splitting, the MapReduce framework divides the large text file into smaller splits, which is often determined by the underlying distributed file system's block size. Because I just now discussed in the beginning that whenever we're talking about the block size, it is 64 MB by default. So generally, we should have that kind of split only. Each split represents a portion of the input data. Right. We come to the now next phase. After we have split the input data, that is, we have identified the input split. The next phase is the map phase. Now, what is going to happen in the map phase? We have a mapper function. The input data chunks are processed by multiple mapper functions in parallel. Now, this is what you have to look forward. So, the data split, it is being processed by multiple mapper functions in parallel, and each mapper takes a portion of the input split and performs the operation, right? So for every split we will be having a mapper. So every mapper will be running every mapper will be executing its mapper function on the input split, and whatever is the mapper function, whatever functionality you have provided in the map function, that will be done, right? So key value emission in the mapper function, the key value pairs are generated as an intermediate result. So the input is also a key value pair and the intermediate result is also the key value pair. So these key value pairs represent some aspect of the data that you would want to process further. So each mapper can emit multiple key value pairs. This I'm going to show you when I take up an example. All in all, you have to remember is we have a mapper function which is going to take the input in the key value pair, and it is going to process and give you the result again in the form of a key value pair. So how do we understand this in a master slave setup? A node which is assigned a map function takes the input and emits a set of key value pairs. So one of the nodes in the cluster, which is a special node, which is the master node, which is going to control all the slaves. So master node assigns the work to the other worker nodes or the slave nodes. And master nodes always make sure that the task is done by these slaves. And it is also responsible for saving the location and the size of each of the intermediate output that is being generated by the map task, right? So see, one phase is the map phase. You give the input, map phase is going to do its work, whatever mapper function you have written, it is going to give you the intermediate result. Now, where to store store that intermediate result. That is obviously stored locally on the slave nodes, and then it will be given for the, again in the form of key value pairs, and then it will be given for execution in the next phase. Right. So this is what, look at this example, assignment to the mapper. So let's say we have a input data. We have divided it into, let's consider three splits only, as you can see here. So we have split 1, split 2, and split 3. Right. Now, how is these split being assigned to the mapper? Split 1 goes to mapper 1, split 2 goes to mapper 2, split 3 goes to the mapper 3. And each of these mappers, again, they are going to work on these split, and they're going to generate an intermediate result. So each mapper processes its assigned split independently, and of course in parallel with other mappers. The mapper reads and processes the text data within its split and performs the desired task. Now let's look at the output. Now we have got the input as a split in the form of key value pairs. The mapper has processed that, and what output are we getting now? Intermediate key value emission. So as each mapper processes its split, it generates intermediate key value pairs based on the data within that split. These key value pairs represent the results of the mapper's process. Right. Now, after you have the intermediate key value pairs from the mapper, then we go to the next phase, that is the shuffle, sort, and group phase. So after the map phase, the framework collects all the intermediate key value pairs emitted by the mappers. The framework then sorts these intermediate key value pairs by their keys. Because output is also, the intermediate output is also in the form of key value pairs. So now sorting will take place. That is the result. It would be now sorted with the key value. This sorting is essential because it groups all values associated with the same key together. Now that means there will be, it will happen after the mapper has executed its task, its processing. It will happen that same kinds of key will be generated with different values. So now is the time to sort these keys, to group these keys, so that एक key के corresponding हमें सारी एक list of values मिल जाए. Right. So now look, let's look at the output of this step. The output of this step is that you have a key 2, that is K2 is the key, and then we have a list of values which are associated with the key K2. So this is the output of this shuffle, sort, and group phase. So what this phase has done, जितनी भी हमें मैपर से आउटपुट आया था, हमने उसको कीज के विद रिस्पेक्ट सॉर्ट करा और हमने उनकी वैल्यूज को कंबाइन कर दिया विद रिस्पेक्ट टू द कीज अगेन. So this is what is the output. Yes, let's look at this example. So let us suppose that we have B1, B2, B3. These are the three book titles. The Quick Brown Fox is B1, B2 is Jumps Over the Lazy Dog, and B3 is the Quick Brown Fox Jumps Over the Lazy Dog. So uh, now the given below, yes, let me mark this. So this is what is the output. What you are looking at the screen is the output. What is happening is you have this key, that is the, and what is the value? It is in the form of list 1, comma 1. So this is how it is going to group it. That is, it has grouped the values depending upon the keys, on the basis of the keys. So lazy 1, comma 1, over 1, comma 1. So this means that out of these three books, it is going to give you the frequency of every word that is occurring in these titles. That's what it is doing. So this is the output again in the form of the key value pair, but it is grouped with respect to the keys. Then finally we have the last phase, that is the reducer function. So each reducer, it receives a group of key value pairs grouped by a common key, and the input to the reducer will be of the form K2 and corresponding the list values. The reducer processes these grouped key value pairs to generate the final output. It can perform various operations such as aggregation, summarization, or filtering depending upon the specific task. So reducers, again, they are going to run in parallel but operate on different groups of key value pairs independently. Reducer processes are executed and all the values are collected against their corresponding keys. Reducer stabilizes the outputs of various mappers and computes the final output. And again, the final output will be of the shape list p-value pairs. Let's look at the example. Now, the input to the reducer is given on the left hand side, and the right hand side is the output. So, what we have got is what input we have got in the reduce phase is we have the key and the list of values. What is the output is that it has aggregated it. Okay, so it has actually added all the values and it has given in the output that this particular word, the, it is occurring twice. Then again, so yes, right. So this is what it is going to reduce. So that is why it is the name reduce. So it is going to aggregate and it is going to give you the final output of the entire MapReduce task. This is how a data flows. So you have this input file, which you can see here on the left hand side. Then input file, it is being divided into splits and it is being read in the processing in the system, and it is being assigned to each mapper. Every split is being assigned to each mapper. Mapper is going to perform its function. It is going to generate the intermediate results which are written on the local disk of every slave node, right? Then they are being given to the reducers, and finally the reducers are going to do their work depending upon what functionality you want them to do, and then they're going to write it to the output files. Now this output, it can be written on the HDFS also. You can write it into a database also, and this can be any this output, it can be to any of the source, different destinations it can have. So let's see that what are the data sources that are contributing. First is the HDFS, that is from whenever you this particular topic says that when you are processing a MapReduce application, a MapReduce program, what can be the different data sources. So HDFS obviously is one, which is a distributed file system that is frequently used with MapReduce frameworks, and it is of course built on Hadoop. It is made to manage and store very big files over a cluster of inexpensive hardware. MapReduce task generally inputs the data into HDFS for processing. Then it could be the local file systems in some circumstances, particularly during development or while working with smaller data sets. You could work with data that is saved locally on the file system. When in production, you can use HDFS. Okay, just to ensure that you have scalability and your entire system is fault tolerant. Then there can be external data sources, that is, in addition to databases, cloud storage, and online services, MapReduce can also access data from these sources. So, like you can, integrate your Hadoop framework with MongoDB, and you can write the MongoDB connector, and you can just then send the data to and fro, processing and sending. MapReduce programming, data access and storage. So when we're talking about the inbuilt distributed file system, that is the Hadoop file system, Hadoop distributed file system, most MapReduce frameworks stores the input data and the final output in a distributed file system like Hadoop distributed file system. These file systems distribute data across multiple nodes in the cluster for fault tolerance and scalability. Then storing the intermediate data, that is after the mappers or the shuffle, sort, and group phase have been executed. So intermediate data is temporarily stored on the local disk of the worker nodes. It's not persistent to long-term storage. So just in case you have a mapper node which fails, so in that case you will have to execute that map task again. Why? Because the intermediate results are stored on the local disk. Output data is stored in the distributed file system. User can also specify the output directory where the results can be saved. The MapReduce programming, data input and output. So data is being read using the input format class in Hadoop MapReduce. So this is the class which is going to enable you to read the data into the system, right? And you can have different data formats. So depending upon what kind of data you want to read, you have to use it. You have to use the desired class accordingly. So the division and reading of the data from the storage system are governed by the input formats. Like if you are using a plain text file, so you are going to use this text input format. If you are dealing with binary files, so it's going to be a sequence file input format. And if you are taking your input from a MongoDB, that's a database, NoSQL database, so you have to use MongoDB input format. For additional help on this, you can contact me later. I'm going to share my contact details to you. Then we have a record reader. So this program reads individual records, that is the key value pairs, from the input formats using the record reader, and it is crucial element of the input process. Why? Because when we talk of giving input, processing it, generating the output, it is all done in the form of key value pairs. And this is the record reader that comes into the picture, this class, which ensures that it is going to read the records in the form of key value pairs, and it is going to generate the desired output. Then, when we talk about data output, after you have executed the task, MapReduce task, so output format classes define how the data is written to the storage system. So common output formats include text output format, obviously for text files. When you are dealing with binary files, again it is sequential file output format, and you can also customize it using the custom output format. Likewise, you can use for MongoDB and for other different data output formats. Then again, like we had a record reader, we do have a record writer, which is responsible for writing the key value pairs to the chosen output format, and it is a fundamental concept of the output phase, because again we have to focus on the key value data structures. Let's discuss some of the use cases wherein we can have MapReduce programming in picture for carrying out a desired application task. So first, and a very simple one, is the word count. A simple MapReduce use case where you count the frequency of each word in a large text corpus. It's often used for text analysis, analyzing customer reviews or social media analysis, sentimental analysis. So if you are focusing on these kinds of applications, you can definitely use MapReduce, and you can definitely use this particular use case of word count. Then we have log analysis, wherein you want to find out certain anomalies in the network, right? So you have to analyze the logs that are being generated from the web servers, application servers, or the network devices. Right. For that case, you can also go for a log analysis using this MapReduce programming paradigm, and it also ensures that performance issues are taken care whenever you are using this. Then for data extraction, transformation, and loading, that is for the ETL operations, MapReduce is often used in data pre-processing tasks such as data cleaning, transformation, and aggregation before loading it into a data warehouse or a database. Then a very upcoming and an ongoing trend is of the recommendation system. So there also you can use MapReduce to build recommendation systems like those that are being used by Netflix or Amazon. It can process user behavior data to generate personalized recommendations for the users. Then another application is the PageRank algorithm, where MapReduce is being used to implement algorithms like PageRank, which is essential for search engines like Google, and it can help you rank web pages based on their importance and relevance. Then you can use it in text mining for natural language processing, analyzing large volumes of textual data for sentimental analysis, topping modeling, or the entity recognition. For that purpose, also you can use it. And image and video processing, because when we are talking about image data or video data, we are talking about very large scale data, right? So processing and analyzing large collections of images or videos such as satellite imagery analysis, medical image processing, or video content analysis, it can also be done using MapReduce. Okay. Let us discuss a problem statement wherein what you are given is you are given a large collection of text documents, and your task is to count the frequency of each word in the entire corpus and produce a list of words with their respective counts. Like if I say I am going, so in this statement, in this sentence, you have to give me the frequency of every word that is occurring. Right. So how can you implement it using the map-reduce programming model that we're going to see? So the input is a, again large text document or collection of documents. And output is for each unique word in the input document. The output should include the word and its count. That is the number of times it is appearing in the document. So for this, we have to write the mapper function, the reducer function. Rest all the intermediate stages like grouping, shuffling, sorting, that is automatically taken care of. Okay, so whenever we are focusing on any problem and whenever we are looking at a solution using a map reduce programming paradigm, all we have to focus is on writing the mapper function and the reducer function. So if you look at the input here, so it is going to be a document or a chunk of a document. Then we are going to tokenize it. That is, we are going to split the documents into words. We have to do some kind of pre-processing. That is, we have to filter out the stop words. Okay, then remove the punctuations, convert it into lowercase. So this kind of pre-processing has to be done. And then it is going to emit as a key value pair, wherein for each word in the tokenized document, it is going to emit a key value pair where the word is the key and the value is 1. Then next phase is the shuffle and sorting phase. After the mapper phase, the map reduce framework groups the key value pairs by key and sorts them. Right, so this ensures that all the occurrences of a word are grouped together and are ready for reducer phase. Then we have this reducer function, wherein we have this input, which is a unique word and a list of counts. Then we have to sum the counts, that is, iterate through the list of counts and calculate the total count for that word. And again, it is going to generate a key value pair where key is the word and the value is the total word count. So let's look at this example. So this is our input. So we are taking 3 documents. This is a simple example and we will use this example to count the words and each word in this example will be counted. So this is our input set. So for this input set, mapper is going to give us the output that for every word it is going to associate a value of 1. This is how we have written the mapper function. You can just go through this. After this, we are moving into the next phase, wherein the map reduce framework it is going to group the mapper output by keys and then it is going to sort them. So this step is going to ensure that all the occurrences of the same word are grouped together. Right? What is happening in the reducer is on the left hand side you can see that this is the input to the reducer and on the right hand side this is the output. So the reducer is going to work on the keys and their values, that is, it is going to group them, and finally it is going to aggregate them. So if you look at the first instance, that is this appeared once only, so the output is going to be this. The word example, it has occurred thrice. Okay, so the list is 1 comma 1 comma 1. It is going to aggregate it and it is going to give you the value of, and likewise for every word in the corpus, it is going to generate the output like in this manner. So if you just want to take a note of this input, you can just do that and you can then just match it. Yes, and so you can just do this example. Let's look at the another problem, that is when we are trying to create a recommender system, we're trying to build a recommender system. And what is that we are looking at? We have to generate computationally efficient recommendations from large scale data. Right. So we will be talking about the introduction objective, the results, and the proposed work. So why do we need a recommender system? Just because we have large amount of data available to the users, and it is leading to the problem of information overload. So continuous efforts are being made to help the user with this problem of information overload. And recommender systems, it solves this problem because it is going to generate personalized content. So recommender system is a software system which acts as a helping guide for a user who is overburdened with information choices and options. It is going to recommend items or products to the user based on users' likes and preferences. So, when we talk about recommender systems, these are the three categories: content-based, collaborative, solution-based recommender system, and hybrid recommender system. Now, what happens in a content-based recommender system is that it is based on the concept, show me more of the same what I have liked. So here you can see we have a user, and we have to create a user profile depending upon what items are being liked by the user, what items are not being liked by the user, what kind of ratings are being given to the items by the user. And then we have the product features, because every item or the product that is there in our repository, it will be having certain features. Now then we are this recommendation component, it is going to find a match between the user profile and the product features, and those with the high similarity will be the ones who will contest for the recommendation list. So we are going to implement this recommender system using the MapReduce programming paradigm. Right. So we will be dealing with the content-based recommendation. Now, what happens in the collaborative is that the target user, we are going to find a set of similar users to him or her, and then the recommendation component is going to work in collaboration with the set of similar users and the target users, and then we will be having the recommendation list. And hybrid is using the advantages of both and suppressing the disadvantages. So this you can just see that there all the two methods are being combined together just to get the advantages of the two. So we are looking at generating item recommendations from voluminous and variety data and overcoming the problem of information overload. Then we have to also ensure that the recommendations that are generated from this large scale data, they are computationally efficient. Just to ensure this, we are going to use Hadoop framework, and we are going to write the source codes in the MapReduce programming paradigm. Right. So the motivation is that first you have to look out for what you can say is a large scale data. That is, it should have variety, it should have volume, then it should have velocity also. So, and not because not anything can be regarded as a big data. Right. So first is that you have to identify that what is big data, why you can say that given this data set it is a big data. The next is developing a recommender system on a distributed computing platform to generate computationally efficient recommendations from large scale data. So we have considered the news items as our large scale data, as our data set to generate recommendations. So events across the globes are happening, and events, they are recorded as news. So the amount of news that is being generated, it is quite high. So it amounts to a large volume of data that is being generated. The news items are generated in different formats. It varies from being structured to semi-structured to unstructured, and it is from variety of data sources, that is heterogeneous data sources. So it also has variety in that. So the speed of generating news is quite high, so its velocity is also ensured there. The news items are collected from from trusted news channels, so the authenticity is somewhere, the trustworthiness factor is always there. And news items are reported about entities that has a high degree of interconnection, because any news that comes about a cricketer can also fall into a sports category, can also fall into an entity category also, right? And if so, the interconnectedness is always there when we are talking about the news items, because it's the events or the yes, these are the events that are reported for the entities or for any such event and things like that. So news data set, it comprises of news items collected from heterogeneous news channels. News items are collected in large amounts using the news RSS feeds. And this is what is the structure of an RSS feed. That is, it is an XML form, and there are different attributes like you have the title, then you have the link, then you have the description. Okay, then you have the channel from where you have taken that news, the date, and all those attributes. So news data, it is a semi-structured data, and news items are rich in textual information represented in the form of documents. So we cannot, simply store it in an SQL database, because, as I told you just now, that news, when we talk about the news data set, it has variety. It has high velocity also, right? It is voluminous also, and since it has no fixed schema, so we have to go for a no this yes, since it has no fixed schema, so we have to opt in for a schema-less database. So that is why, keeping in view all the attributes that a news item has with itself, we are opting for a document-oriented NoSQL database, that is a MongoDB. So data in MongoDB, it is stored in the form of document, set of key value pairs, and it has got a dynamic schema. So it is able to cater to unstructured data, it is able to cater to the semi-structured data, and it is also capable of storing the structured data. So several documents are grouped together to form a collection. So we say we have a collection of documents. So this is just a snapshot of, though NoSQL database is another processing technology for a big data, because it is scalable also, and it has all the fault tolerant features and parallel processing and everything it is catering to. Right, so this NoSQL, when you combine it with Hadoop and you do the processing, it makes an excellent framework for a lot of applications. So this is just a snapshot of the user data. So on the left hand side that you see here, so we have created the database with the help of the news portal, and in that we have collections like the news data and the user data. So news data is storing all the data with respect to the news, and user data, since we have a recommender system, so you have to go for a user profiling also. So that user data is present in this user data collection. So this is just a snapshot of the user data collection. So you can see that it is again storing the data in the form of key value pair. Like here, the ID is the key and the value is 3. Then again we have username as the key and the value is Anjali. So likewise, this we have the news items that are being read by that user is also given as a list, as a list of news items, okay, along with their IDs. So this particular user has not given the rating, so that is why you can see that the rating parameter is missing here. But just in case the user has rated the item, that is also being captured here, just because we have to do the profiling. And this is the news data item. So all the news, they are being collected in the news data collection, and depending upon whether it's semi-structured or structured, it doesn't matter to us, because we are focusing on the schema-less database. That's a NoSQL uh, MongoDB database. So generating recommendations from a large scale data requires developing a recommender system which is computationally efficient, and also it should be accurate, right? So when a user is posed with a lot of data, how will you ensure that he is being recommended with items which are of interest, number one. Number two, which are also efficiently computed in terms of time. Because if you are just focusing on the results, on the accuracy part of the system, and let's suppose it's taking a lot of time to generate them, so it is simply going to annoy the user. Right, so for that we have used Hadoop, which is an open source framework hosted by Apache, and which is designed to run on the distributed system using map reduced programming paradigm, and data it is residing in the HDFS. And obviously we are going to use the map reduced programming paradigm, which consists of the mapper task and the reducer task. So data, it will be again processed in the form of key value pairs. So this diagram I've already shown you. We have in this particular research problem, we have created a cluster of 3 nodes of single node and a cluster of 5 nodes. So depending upon what is your application, how much data you want, how much faster processing you want to take, you want it to happen. So you can have as many number of nodes in that cluster. So this is the master slave architecture. The corresponding parts of the map reduce and the HDFS is being shown. This we have already discussed. Now this is our recommendation algorithm, the framework. How are we going to do this? We have a set of all documents. Since we're talking about news documents, so these are purely textual documents. Then we are going to extract feature values from them. Right, so document feature extraction is one process which is going to generate a feature vector. Right, that is going to generate a feature vector for every set of documents. So, like if you have, I hope you know the feature vector. Okay, for this process, we have used the term frequency, inverse document frequency concept, that is TF-IDF, for converting all the documents into a feature vector, right? And then we have a similarity, and on simultaneously we have the user. User is going to read the documents, though he might not read the documents, but what we have taken is that if he is spending some amount of time on that particular article, so that might be of interest to him. But outliers like logging in and moving out, that he just forgot to log out, or he has just opened the screen and he is doing something else simultaneously. So outliers like this have also been taken into consideration. And once we know that the user has rated a particular item or explicit rating or implicit rating, so then for those items again we are going to compute the feature value using the again TF-IDF concept that is implemented in MapReduce. And this way we are going to create a user profile, right, based on the feature vector, and then we are going to compute a similarity between the documents that are not being read or that not being seen by the user and the documents that are being seen by the user. Okay, so we are going to match these feature vectors using the cosine similarity. Again, that is implemented in MapReduce. And we are going to find out that what items are similar, what unseen items are similar to that of the user, and those will be contesting for the recommendation list. So we have the MapReduce content-based recommendation. It consists of 2 parts. That is MapReduce space vector space model. That is MRVSM, wherein we are going to vectorize the documents. We are going to create a feature vector. And then we have the MapReduce based cosine similarity, where we are going to compute the similarity between the vectors. So MRVSM, that is vector space model, it is used for user profiling and for document feature extraction. For every document that the user has read and for every document that he has still not seen, we are going to convert them into feature vectors, because eventually every processing has to be done in numbers, right? So that is why we have to convert all the textual data into numbers. For that, we have gone in for feature vectors, creating the feature vectors. Once we have the feature vectors, then we're going to compute the cosine similarity, and then obviously document filtering will happen. So this is our proposed framework. So we have the content providers, which are nothing but the RSS feeds. We are going to download the news from the various RSS feeds that we have with us, and that will be loaded into MongoDB, which is a NoSQL database, a schemaless. And then from NoSQL database, the data it will move into the Hadoop cluster. So for establishing this connection, that is between the Hadoop and the MongoDB, I have written a MongoDB Hadoop connector for that, right? Just to ensure that a free flow of data to and fro can happen. And once the data is in the Hadoop cluster, so we have used the MapReduce and HDFS for processing the data. So MRVSM, that is vector space model, it is used for feature extraction and for user profiling. And document filtering is done by executing a cosine similarity between these feature vectors. And then finally, we have the recommended documents, which are given to the user, and if the user is going to rate the documents, that will be updating the user profiling, and if it's not going to do it, then also it's fine, we are doing it implicitly. So feature extraction process, it involves identifying relevant set of keywords which represents a document, and documents are pre-processed using the standard technique of stop word filtering and stemming. So this is a standard technique when we talk of natural language processing, that is we have to remove the stop words and we have to actually boil down to the stem words for every word, right? So these are the two pre-processing techniques that we have used. And map reduce based content based recommender system creates map reduce based vector space model for document feature extraction and for creating user profiles. MRVSM uses term frequency inverse document frequency, that is TF-IDF, for weighing the terms within a document to create a term vector for them. So the vector space model for user profiling and document feature extraction is described as this. So we have a vector space model for every news item it will be done. Okay, so if there are let's say 1,000 or 10,000 news items, for every news item we are going to create this term vector that will be represented by the term and its weight, that is TF-IDF score. Then the second term for that news item and the TF-IDF score. So likewise, if there are 10 terms, so for every term we are going to, obviously after removing the stop words and doing stemming, then we are going to complete this vector space model. So for every term, we will be having the term followed by its score. So where term frequency is given by the number of times uh, a term appears in the news item divided by the total number of terms in the news items, and IDF, just to reduce the popularity, we are using this formula for IDF. So using MRVSM users profile, an entire corpus of documents are expressed as term vectors. Recommendation is then finding the similarity between these two term vectors, what is being read by the user explicitly or implicitly rated, and what is being not seen by the user from the entire corpus of the document. So MRCBR, it uses MapReduce based cosine similarity to find the cosine similarity between these two term vectors, and we are going to use this formula for the cosine similarity. And after filtering the documents at this particular point in time, wherein we are going to find the cosine similarity, we are going to give the top n items as the recommendation for the users. So this is one thing that we have done, and this is just these are just two use cases that I have discussed with you. But as I have shown you in the previous slides also, that there are a number of applications wherein you can use this MapReduce programming paradigm to generate your applications, and it would be way faster, and the different set of programming languages that are available to you for developing the program is also being shown to you, right? So that's all from my side for this session. So if you have queries, you can ask me, and if you feel that at some particular point later in time you will have queries, so you can just write down my email ID and you can write to me for any of the queries.
Thank you so much, ma'am. It was a nice session. Any participants, if having any queries, then please raise your hand and you can ask the query directly. You can just raise your hand, you will be given the mic to speak on. For any queries, please raise your hands.
Ma'am, there is one participant who wants to, I think, ask something.
Okay, you can, you are able to. You can unmute your mic. You can unmute your mic, sir. Your permission has been given to you, Rakesh sir.
Good afternoon, ma'am. Good morning,
Good
ma'am.
afternoon. Good morning.
Ma'am, I want to know. I am a Java programmer. I want to know some special API or for the Java if to work on the Hadoop. Is there any?
Yes,
Please
sir.
help.
Yes, sir. Yes, we do have, because see, when we're talking about MapReduce, so there are certain, like I just told you that there are certain input format classes that you will be working on depending upon what kind of data you are handling. So definitely there are set of APIs, and that list I think I will share with all the participants, right? So I will give it to the coordinators, and then they can share with you all, and you can use them. No problem. Java is a very well supported language, because I myself have done it in Java, all the implementation on MapReduce. So all the libraries, APIs, and everything is well supported there. So I'll just share that.
Okay, okay. Thank you, ma'am. Please, sir. Okay.
Yes, Alok sir, you can continue with your query. You have been given the mic.
Okay. Good morning, ma'am. Alok Mishra
Good
this side.
morning. Good morning,
Actually,
sir.
ma'am, I have a query. As we know that Hadoop, a solution for big data. Okay, and
Yeah.
we have a cluster to perform security levels and all. Okay, so I have a query related with the file permission. Is SDFS implements any interface to handle this? We can.
See,
I see how it handles. Hadoop, how it handles.
so you're talking about the file permissions, right?
File permission,
File
because
permissions.
yeah,
Yeah, please go ahead.
because presently I'm working on Hadoop and all, so I
Okay.
just wanted to know.
So how is it being handled? This is what you want to know.
Yeah.
Yeah. So see, definitely when we are working with Hadoop, when we are working with HDFS, so these features like file permission, the access control, and everything, these are a part of the ecosystem, right? So when we are talking about the file system, so see, if you are an owner of the file, so definitely you will have the permission to read or write. So how about granting the permissions to all other users who are still not the owner but they want to use? Yes, whenever you are doing the installation, it is then you will have to set up those file permissions.
Okay, so
Have, have you installed? Have you created a cluster or maybe a standalone ecosystem in that case? Have you done that?
same thing happens like in Linux owner group and others.
Yes, same ways, because read, write, execute, so RWX, same all those concepts that applies to the Hadoop file system also. Like if you are accessing the files within the directory, so you should have the permission for the directories also, and then the corresponding files or the entire directory, depending upon how much access control you would like to have for the owner and for the other users also. So same commands are being used, like you have the list command, right, which is supported in Linux. So ls. So that command also run here. So for the root directory, the same concept. So everything it goes in parallel, right? Is it that you're looking for some specific commands? So I can tell you, or
was looking for. I just wanted to relate it with the
yes, if you want to do that mapping, that is there. That is the same.
during the session you discuss about the interface and all. So that's the reason I relate.
Yes, yes. So if you're well versed with Linux, so you will not be having problem using the Hadoop file system.
Okay, thank you. Thank you.
Any other participants who want to ask can directly ask the queries. I think no other participants are there, Anjali ma'am. Thank you so much for your valuable time. The session was very nice and you have simplified the big data research trends. Your research case studies have enlightened us very much and we can proceed now in the right direction in the same domain. So I really thank you for spending your time and sharing your valuable knowledge. Thank you so much, ma'am.
Thank you, ma'am, for giving me this opportunity. I would like to thank the entire organizing committee and the director of the institute for having given me this opportunity to enlighten the participants. And if anybody is interested for collaboration or for research guidance or some any kind of help that I can provide, so I will be really happy to help the participants and others. So you can write to me and then we can go ahead.
Sure, ma'am.
Thank you
Sure.
all the
Thank you so much
participants.
for your support. Thank you so much.
Yes, ma'am. Thank you.
Now I request all the participants. There's a lunch break. We will join. We will meet again at sharp 1 p.m. So I request all the participants to join at 1 p.m. sharp. Thank you all the participants for your time.